frequencies on both sides of the resonant frequency. Resonance means frequency matching. This is the classical condition for electrical resonance. Now, what is this sharpness of resonance? Hello students, let us continue our discussion on alternating current. In my today's session, we will be dealing with a very important phenomenon, a very classical phenomenon, what we call as electrical resonance. And once we understand what is this electrical resonance, we will derive an expression for resonance frequency, or what we also call resonant frequency. Fine. So now we start understanding a basic phenomenon called electrical resonance. Now, what is this resonance? In your first year, when you studied the chapter oscillations, we discussed concepts like forced oscillations, damped oscillations, resonance, etc. Where we told at resonance, the natural frequency of oscillations becomes equal to the applied frequency. Again, I repeat, at resonance, the natural frequency of oscillations becomes equal to the applied frequency. Andre, what I want you all to remember here is the word resonance means frequency matching condition. This is all I want you all to understand now. Resonance ಅಂದ್ರೆ ಯಾವುದಾದ್ರೂ ಎರಡು ಫ್ರೀಕ್ವೆನ್ಸಿಗಳು ಮ್ಯಾಚ್ ಆಗೋದು ಅಂತ ಅರ್ಥ. ಫ್ರೀಕ್ವೆನ್ಸಿ ಮ್ಯಾಚಿಂಗ್ ಕಂಡೀಷನ್ is what we call resonance. You have done your sonometer experiment. You have measured the resonating length. Resonance means frequency matching. There is one more term which we commonly use called coherence, where coherence means wavelength matching. So here, all my discussion is about electrical resonance in a series LCR AC circuit. How resonance can be achieved in a series LCR AC circuit is all that we study in today's class. Now, my dear students, previously we defined something called as inductive reactance, denoted by XL. An inductive reactance andre, we told it is the opposition offered by the inductor to the flow of AC current, and we wrote XL is omega L. What was omega? Remember my derivations in the previous class. Angular frequency, omega was 2 pi f. Therefore, this is equal to 2 pi fL. What I want you all to understand here is XL is directly proportional to the applied frequency. Point number 1 in my today's class, XL, which is nothing but inductive reactance, is directly proportional to F, which is the applied frequency. Similarly, we studied capacitive reactance, XC, which was 1 by omega C. And what is capacitive reactance? Opposition offered by a capacitor to the flow of AC current. And this is 1 by 2 pi FC. Here what I want you all to understand is XC is inversely proportional to the applied frequency. So XL is directly proportional to the applied frequency, and XC is inversely proportional to the applied frequency. Keeping this in mind, I am plotting a graph of the applied frequency, x-axis applied frequency, y-axis it is XL or XC. So I have the applied frequency along x-axis, and along y-axis I have XL or XC. First case, how should XL behave with respect to frequency? You'll know the relation. They are directly proportional. So, as the applied frequency increases, the value of XL should also increase linearly. Yake? They are directly proportional. Increase the applied frequency, XL also increases. But what should happen to XC? XC is inversely related. So, if you observe here, as the applied frequency is increasing, XC is decreasing gradually. So, as you increase the applied frequency, XL also increases linearly. And as you increase the applied frequency, XC decreases gradually. But if you observe the curve, this is very important. For a particular frequency, at some specific frequency, characteristic frequency, what I call as F0, please to observe here, XL is becoming equal to XC. So at this point, for a particular frequency F0, XL becomes equal to XC. And we say resonance is achieved. So at resonance, therefore, very clearly I am making a statement. At resonance, what should happen? XL should be equal to XC. Please to understand, students, this happens only at a particular frequency F0, and this particular frequency is what we call resonant frequency. So, what is happening at resonant frequency? XL is equal to XC, and hence we say electrical resonance is achieved. What is this electrical resonance, students, then? If you go by this statement, for a particular frequency of the applied voltage, it doesn't happen at all frequencies. At a particular frequency, a specific frequency, what we call as resonant frequency. That particular frequency is called resonant frequency. What should happen at resonant frequency? Please to understand, the impedance of the series LCR circuit becomes minimum. Now, what is this impedance? Go back to my previous derivation. I have derived an expression for impedance. What was impedance? It was the opposition offered by the inductor, capacitor and resistor together for the flow of AC current. So whenever resonance is achieved, that impedance, that opposition to the flow of AC current reduces, and hence current flowing through the circuit is maximum. And this is what we call electrical resonance. So what is electrical resonance? It is a phenomenon, a process which is classically observed in a series LCR AC circuit, where for a particular frequency, what do I call that frequency as? Resonant frequency. For that particular frequency, impedance of the circuit breaks down. The impedance of the series LCR AC circuit becomes minimum. Opposition to the flow of current is minimum, and hence maximum current flows through the circuit. Now, we will now derive an expression for what we call resonant frequency. So we told at resonance, whenever electrical resonance is achieved, XL should be equal to XC. This is the classical condition for electrical resonance. XL becomes equal to XC. Now on substituting, what was XL? 2 pi FL omega L. XC 1 by 2 pi FC 1 by omega C. Now what should happen to this F? The moment XL becomes equal to XC, the moment you say electrical resonance is achieved, F should be equal to F naught. Only when there is F naught, resonance is achieved. And this F naught is called resonant frequency. So instead of F, I substitute F naught. So this F naught goes to the numerator. Elli F ide, alli F naught and substitute ಮಾಡ್ಕೊಂಡಿದ್ದೀನಿ, where F naught is called resonant frequency. Now, F naught goes to the numerator on the left hand side. F naught into F naught is F naught square, which is equal to 1 by 2 into 2, 4, pi into pi, pi square, L coming to the denominator, and C. Or we write, taking square root, F naught is equal to 1 by 2 pi root LC. This is the classical expression for resonant frequency. F naught equals 1 by 2 pi root LC. And therefore, if I infer here, if you observe, the expression for resonant frequency is independent of the resistance of the circuit. R term illa. It depends only on L and C, and it is independent of resistance. Now, as we concluded, maximum current flows through the series LCR circuit for a particular frequency called resonant frequency. Why? At resonant frequency, resonance is achieved, impedance is minimum, opposition to the flow of AC current is minimum, so maximum current has to flow. Resonance phenomenon is exhibited by a circuit if both inductor and capacitor are present in it. I don't want a resistor, but I want that LC combination. Why? Very clearly, F naught is 1 by 2 pi root of LC. This LC combination has to be present for electrical resonance. And such series resonance circuit is called acceptor circuit. Now, we will try to understand something called sharpness of resonance. Now, what is this sharpness of resonance? How sharp the resonant curve is? How blunt the resonant curve is? What are the factors which decide the sharpness of the resonance curve or the bluntness of the resonance curve? Now, a graph of frequency of the applied voltage and current is called resonance curve. What is resonance curve, students? It is a curve that is plotted, a curve that is obtained by plotting frequency along x-axis and current along y-axis. Now, we have I naught equals V naught by Z. I equals V by R baritivallva. Ade reeti I naught equals V naught by Z. Where what was Z? Impedance of the circuit. And that impedance, you remember, we derived the expression as Z equals root R square plus XL minus XC whole square. Madidini derivation in my previous session where Z is equal to root R square plus XL minus XC whole square. Now what happens at resonance? XL should be equal to XC, which means this term cancels out. Naturally, the feature of resonance, XL should be equal to XC so that Z becomes equal to R. So, please to understand, students, at resonance, wherever there is resonance, Z becomes equal to R. And therefore, maximum current at resonance is I naught or I max is V naught by R. I repeat, wherever resonance is achieved, XL should be equal to XC so that Z becomes equal to R. So maximum current should be V naught by Z didn't baradnalva. Z is now replaced by R. This is the game now. Our resonant frequency may be independent of R, but maximum current depends on R. In the expression for resonant frequency, resistance never came into picture, but wherever there is resonance, current depends upon resistance, which means as R increases, the value of current decreases. So, if you can see here, the graph R1, R2, R3, three resistances where R1, greater than R2, which is greater than R3. Value of R1 is more than R2. Value of R2 is more than R3. So as R increases, current should decrease. So R1 is more sharper. R2, the sharpness slightly reduces. R3 again reduces. Here, F1 and F2 are called half power frequencies. Frequencies on either sides of the resonant frequency. Frequencies on both sides of the resonant frequency. Yen karitivi? Half power frequencies. And that F2 minus F1, difference of the half power frequency is called bandwidth of the circuit. What is bandwidth? It is the difference of the half power frequencies. Therefore, if the bandwidth is small, sharpness or the quality of the curve is more. Next, I come to that quality factor. If the bandwidth is more, quality reduces. Therefore, we say delta F is F2 minus F1, which is called bandwidth. So you have to remember here, resonant frequency may be independent of resonance, but sharpness of the curve depends upon resistance. As the value of resistance increases, current flowing through the circuit should decrease, sharpness should decrease, quality decreases. So my dear students, in today's class, we have studied something called resonant frequency. At resonance, always remember, XL should be equal to XC and Z should be equal to R. We derived expression for resonant frequency, which was independent of resonance, and we discussed something called bandwidth and sharpness of the curve. My next session, we will study quality factor and transformer. Until then, stay tuned. We will come back in the next session. Thank you.